Okay, good morning. We're going to talk about ensemble methods, random forest in particular. All right, these methods are pretty much, at the broadest sense of the explanation, you just take a bunch of trees and you take the average of those. All right, so with random forest, that's what you would do. You take a whole bunch of them, right? And that helps in a bunch of different ways, all right, especially for overfitting or for variable selection or model validation. So there's a lot of really important parts to ensemble methods. Ensemble really just means doing a whole bunch of models and kind of doing majority vote or taking the average of those results. So let's get a little bit more specific here. We'll walk through some examples. So that's what I said at the front. Again, it's just basically an aggregation of a bunch of different algorithms, right? Often in solving a machine learning problem, I hate just to read, at the end of the process, the approach you take can be combining a whole bunch of different predictors, right, and even different models, all right, together, and they work better together than they do separately, all right? We're going to focus on random forest. It's mostly, a bagging model. All right, if I can get my little pointer to work here. All right, it's mostly bagging, all right, but we're going to talk about what boosting is too. All right, there's kind of just a few critical processes, I think I spelled this wrong, that you have to know associated with how random forest works. Right, two of the really important ones are about kind of bootstrap aggregation, which is a bagging method. All right, and then basically the selection of a smaller amount of features at each leaf node. And what that does is it creates a variability associated with how the trees are grown, and that allows them to work better together. All right, so we'll talk more about that. All right, you can also do it where you're building several models that are just different models, not the same models. Like random forest is a bunch of decision trees, but you can also do it where you're building a KNN, a logistic regression, a support vector machine, and a decision tree, right? So this is a very simple example, right? So here what we see is a bunch of different models, and we have a prediction. Say this is just row one, right? Or row one. I don't know why I had to write that out, but say it's just row one, right? And three of the four models are predicting that this particular row belongs to class one. All right, so that's what it would be. It would be class one. All right, so this is the majority, right? And all the others are the majority, right? And the idea is that they work together, given the different ways that they train, compensate for its weaknesses, and then select by majority vote, hard voting in this example, the one that works the best. All right. This is usually a good approach for if you have a whole bunch of weak learners, right? So if you have a bunch of models that aren't working very well, right? Like their capacity to predict is pretty bad. Sometimes if you put them together, it's pretty good. All right. So because they learn things very differently, the way KNN builds a model is very different than the way a support vector machine or a decision tree or logistic regression. So as a result, they have a tendency to learn differently and can compensate for each other's weaknesses. All right. So how does this work, right? So essentially scale, right? By scale, we mean the number of models, all right, increases the probability of finding like a true majority vote. All right, we know this because of, probabilistic theory, right? Associated with how we would say determine if a coin is fair, right? So the number of times you flip a coin, right? The more times you do it, you're going to gravitate towards the mean, and you're going to end up at like this 50-50 split. All right, now depending on how hard it is for the particular model to learn that particular features to predict the target variable, it might take longer, right? You might have to do 10,000 trees or 1,000 trees. In this example, 1,000 coin flips or 10,000 coin flips, right? If you get to 10,000, you kind of get a 90%, 97% chance, all right, of getting this right in terms of like the actual split, which is 50-50, okay? So it works the same way with model building. So this is an example here. We're actually going to build this chart with some of the code in class, and I'll show you, the variability associated with the error rates and then how they change as the number of trees grow, right? So on the bottom here, instead of coin tosses, we would see trees, right? And then over here, instead of the ratio of the number of heads, what we would see is just the error rate associated with how the tree is growing, right? The misclassification area. We could just put the accuracy over there. We could pick whatever we want, okay? So here what we see at the beginning, right? Whoa, when we're first just getting started, there's just a significant amount of variability. It's all over the place, right? And then eventually what we see is it starts to stabilize, okay? Across all the examples, here's running many different examples of the coin flip. It starts to gravitate towards the mean, right? And this is still really stabilized kind of way out here around 10,000. Even up here, there's still some variability, and here a significant amount. So that's the idea, right? It's kind of the more you do a thing, the more you get to the truth, right? And that's a real risk with doing just one decision tree, is that it's so non-deterministic in terms of the way that it works. It could be subject to error. But if you do it many times, right? We do these over and over again, it just compensates for that risk, right? That's essentially it, okay? So I said this a bunch of times. Instead of one tree, it's building a whole bunch, all right? We can limit the growth of the trees with some hyperparameters, but we don't have to, all right? So we can set the number of trees, you know, and the grown, and as they grow, and then track the error classification. Then we get a kind of an idea about where our model starts to stabilize, right? And that's actually, we want to pull it back and kind of sit right at that space, all right? We can use it again for both regression and classification. And again, it's mostly kind of boosting and bagging, okay? All right, so let's talk about that a little bit. Tree boosting, bagging. All right, so bagging, so the goal here for bagging is akin to controlling overfitting, all right? So it's designed to reduce variance. So overfitting is akin to high variance, all right? So what we want to do is we want to create simpler decision boundaries, all right? So we can grow a whole bunch of, again, I need to work on my spelling. We can grow a whole bunch of trees, and we can use the distributions of those results to make predictions. I'm sorry, these are fuzzy. I pulled these from another slide. Okay. So what we're doing down here is that what we're trying to do, all right, is compensate for this particular overfitting. You see here, right? If we do just one tree, right, it'll probably, you know, it'll notice that there's a point here, and it'll learn that and just assume that everything underneath that particular point is blue. Well, in fact, it's not true, right? We see that actually the territory right below here is almost exclusively red. All right, so if we ran the same algorithm, here we're just trying to predict like the alcohol and wine. All right, so here what we're doing, we run this algorithm a whole bunch of times, right? So instead of doing just one tree, we do a bunch of trees. What we see is that it learns this pattern better, all right? And that it can compensate for this. And so it actually makes the decision boundary, all right, less specific, all right? So it increases kind of the generality of it, all right, which helps us reduce the variance of the prediction, okay? So that's the goal there, all right, is to reduce that variance. So just let's talk about bagging just generally, all right? This is kind of a klutzy graph, but all right, so as we discussed, you know, there are several methods, and you can combine them together, all right? But one was a much more common way, to be honest, because doing a bunch of methods can be computationally pretty expensive, all right? Is just to resample, okay? And that's all this is. So resampling is akin to bagging. So you'll go back and you'll resample with replacement. And what that means is that every row inside the data set is subject to be sampled at every sample, all right? So we don't take, you know, the first 10 rows, the next 10 rows. After that, it's just random. We say, hey, just take 10 rows out of the entire data set. 10 is way too small. You do more like 100. So take 100 rows randomly, and some of those rows can be sampled over and over and over again. That's fine, all right? But the idea is that each one of the samples will be variable enough, will be different enough from each other to create different trees, all right? So that's one way to control, to what we want to do is increase the variability of the types of trees that are growing. So we know that even in all these different trees, you know, what are the best features to use, what are the best splits to use, and how do we classify particular rows given across, you know, say thousands of trees, all right? So we can do that. And so this is just an example. Say this is our data set here, right? And so here we're sampling different rows, all right? And then we're taking all these results, right? Or here's the sample, I'm sorry. And we're putting out here, and then we're building different trees, okay? This might be an easier way to look at it, all right? So this is without replacement, all right? So we did this way, this would be without replacement, all right? So we would just randomly sample, like the rows might be in different order, but it would be the same 3 rows, all right? These are the same 3 rows. But here, with replacement, we might actually have duplicates. Like in this sample, right? We have 2 of number 1, which is fine. Okay? So we're sampling with replacement, which means that every row is available. Every time to sample, some will be included and some will not. All right, and what this does, if we were to do the same one over and over again, maybe this is obvious, right? We would end up with the same tree. We'd have the same oak tree every time, right? So we don't want that, all right? We want some maple trees here. We want some pine trees, all right, along with our big oak, okay? So they're grown differently because the samples are different, okay? And what this does is it helps uncorrelate, right? It discorrelate the trees from each other, right? There are 8 trees that are very different. But that's not the only thing that needs to be done, all right? So bagging was introduced kind of in the early 2000s, but then in the mid 2000s, Bremen and others introduced another feature associated with decision trees, research with random forest, actually created random forest, which allowed them to be the really useful algorithm that they are today. And that kind of akin to boosting, which means that they would take a subset, right, of the features that are available and also a subset in combination with a subset of the samples. All right, so say you have 20 features. And so what you would say is at every decision point in the tree, the algorithm only has access to 5 of those randomly selected features. All right, so it just randomly selects 5 at each node, and it can use those to build the tree. Okay, so this increases again is another way, all right, for us to increase variability in the trees and allows us to better understand which features are working and create a more productive ensemble, right? The more different the trees are, the more we learn from them. So that's the idea. So we subsampling again the number of features that we have, and then we're also sampling, all right, the number of the data, basically, right? So we're bagging the data, okay? This helps us reduce bias, all right? All right, and it works against underfitting, okay? So we have a tendency to underfit the model here, all right? And so boosting kind of guards against that. So here, what we're seeing, right? So this would just be one decision tree, all right? You just kind of make a broad statement, right? It's just underfit, right? Say, oh, everything kind of below this line is going to be red and everything above here is going to be blue. Well, that's not really true, right? What we see is that it's obvious that red is not beyond this point, okay? So ADA boost, adaptive boosting is a method, all right, that can guard against that. So we deploy that. We'll talk a little bit more specifically about that method in particular. But what it does is it kind of carves off this point, all right? And so it makes the model more specific. So it increases the decision space and moves this blue over here, okay? All right. So these two things work together, right, in combination to make random forest a really effective method for prediction, all right? So it's mostly a bagging model, all right? It actually doesn't do kind of adaptive boosting. I'm happy to talk about that, but it does select subset features, which is kind of a boosting methodology, all right? But these two things work together in combination. So bagging kind of reduces the variance associated with the models, and then boosting reduces the bias, all right? So that allows it to be really powerful because it controls for those two things. Those two things work together in combination too. Primarily, the intention of those, all right, was again to create more variability associated with the types of trees that have been grown, all right? As a result, what happens is that you need actually a lot more trees, all right? Because there's so much variability between them. You know, kind of the default for random forest is 1,000 tree models, all right? But depending on the complexity of your features or the size of the data, all right, you might have to go way beyond that, you know, so maybe out to 10,000 or 15,000 trees in order to be able to get some stability. And I'll show you how we track that. It's not that dissimilar to what we saw in the coin flip, right? Okay. So the main tuning parameter, all right, for random forest is going to be myTry, and that's the number of variables that are available at each decision node for each tree, all right? So the kind of, I think the standard here is just to take the square root of the number of features that you have, right? So if you have, you know, 20 something features or 16 or something easier on myself, then you start with 4, right? And see how that works. And you can adjust that up and down. And the goal here would be to reduce the error quicker, right? So we increase the number of myTries, it increases the complexity, but it also might reduce the error quicker. So That's how we tune that up and down just based off the number of trees that it takes based off that my tribe. Okay? All right. So variable importance, we've talked about this before. The nice part about random forest is much more robust because it has so many more trees to measure against, right? So its ability to select the most important model is really good. It does it similar to what we've seen in the past, all right, where it will aggregate across all the trees that are built using something called the out-of-bag error. So the out-of-bag is the sample that was not used to build the tree. All right, so it'll build the tree, then it'll predict with the out-of-bag error, all right? And then for every one of those trees, it'll aggregate using the out-of-bag error, the total reduction in impurity at each node associated with each one of the features, and then aggregate that together, and that will give us the variable importance. So it tracks basically the utility of each one of these features for every tree that it builds, all right? Based off the optimization function. And typically that's Gini, I think we're using Gini ratio, all right, in this default package that we're going to use, and I'll walk through that, all right? So that's it. So again, it's pretty quick. It builds principally off what we've done. We did clustering last week, that was unsupervised, but it builds off what we did basically the previous 3 weeks in terms of the tree-based models, right? And just builds a whole bunch of them. But we incorporated these new features in terms of bagging and subselecting our feature space, all right? And then we have to think about kind of the complexity and how many trees we want to grow over time until things start to stabilize. So Random Forest package in R is basically just a wrapper for the original Bremen and Cutler. They're from Berkeley, of course. And then the original website is really useful too. They still have all of the original documentation up there if you want to check it out, okay? So quicker video this week, and I'll see everybody on Thursday, and we'll jump into some code. All right, thanks.